All right, section 8.4. So we talked about central angles. And what was true about a central angle? It was equal to its what? Its intercepted arc, okay? That means where the angle goes out and hits the circle, makes that arc, okay? It's equal to its intercepted arc. But now we're going to do another, let's see, that didn't copy. Now we're going to do another kind of an angle inside of a circle, but it's not going to be the central angle this time. And let me put a little center right there, okay? So watch this. What if I don't start from the center of the circle, but I start actually on the circle? So I'm going to make an angle, and it doesn't even have to go through the center at all right? So what if I make an angle where the vertex of the angle hits right on the circle itself? See this angle right here? Take a wild guess. What do you think that angle is called? An inscribed angle. Very good. It's right there. It wasn't much of a wild guess, was it? All right, so it's an inscribed angle. So this is an inscribed angle. So what do I know about an inscribed angle so far? The vertex of the angle is where? It's not inside the circle. It's on the circle itself. Okay, watch. Since you said that, I'm going to do this. Let's do this in a different color so they all stand out a little bit. Okay. Is that an inscribed angle? Why not? The vertex is where? It's inside the circle. It's not where? On the circle, okay? It's only an inscribed angle, and it's very important because we really don't have any theorem that talks about an angle like this where the vertex is inside the circle, okay? We don't have any theorems like that, but we do have a theorem that we just talked about in 8.3 that was this. What was this kind of a angle? This was a what? This was a central angle. Well, it still is a central angle. I don't know if it was, but we talked about it. So this is a central angle, and then this is what? An inscribed angle. Got it? See the difference? Now, what did we know about the central angle as far as like the measure of the angle and the arc that it cuts off? So this arc from here to here, what would it be equal to? It'd be equal to its, well, the arc itself. It's not equal to the arc. It's equal to the central angle. That's right. Okay, so on a central angle is equal to the arc. So let's put a number in here. Let's say that's 40 degrees. So if this angle is 40 degrees, what is this arc from here to here? That's 40 degrees. Everybody got it? Okay. Now, what we're doing today, though, is not the same thing. It's different. It's an inscribed angle. So let's think. Let's just guess. Let's just take a wild guess. And this is kind of a wild guess. I'm not really going to go through and show you exactly why this is true. Let's see what I'm doing next. I think I'm going to skip that little next part right there. It's not that important. All right, but let's do this. This kind of is what we're talking about. Let's just take a wild guess. If this was, I don't know, what does that look like? 30 degrees? Let's say that was 30 degrees right there. What do you think this arc is compared to this arc? It's double. Exactly right. Was that just a guess or did you look? What? You look? That's fine. It's fine. I don't mind you looking ahead. All right, so if this was 30 degrees, this arc right here is going to be double what the angle is. So give me the number. What is this from here? I'm not putting letters in here right now, but from there to there would be what? 60 degrees. Vice versa, right? The converse is true, right? Simone, you getting all this? Yeah? You see better with your eyes closed? So 60 degrees. What if I told you this was 60 degrees? What's the angle? The angle is half of the arc. So you could look at it either way. The arc is double the angle, or you could say the angle is half of the arc. Make sense? Yeah, that's pretty easy. Let's do an example. And I'll just keep this circle here, get rid of all this mess. And get rid of this dot, get rid of this dot. Might have been quicker if I would have just rewritten a brand new circle, but that's okay. All right, check this out. Actually, I don't even need the center. Hold on. Sorry. Okay. So stupid. What's it doing? Okay, I'll keep the center there. I can't get rid of the center. That's all right. So what if the center really has nothing to do with this? So I'm not going to worry too much about it. What if I had this right here, and I'll call this Z. I'll call this 55 degrees, and then watch this. This kind of leads up to the next theorem that we're going to talk about. What if I go to here, and I go to here? Actually, nope, this doesn't lead up to what we're going to talk about. This is something different. I thought they were going to do that. But all right, so that's that. They tell you that this is 60 degrees right here. They tell you this is V, this is W, this is X, and this is Y. All right, there we go. So what they're going to do, they're going to ask you a couple questions. The first question is, find what angle VYW is equal to. All right. Then they have a second question, and they say, what is arc WX? All right, let's take a look at it. Let's change colors a little bit. So they ask for angle VYW. Where is VYW? VYW. So they're asking you to find that little angle right there. Super easy. So somebody tell me it's 30. Exactly right, because you look, see what arc does it cut off? This angle right here, it goes to V and it goes to W. Well, I know that arc, that's 60 degrees. So if that's 60, the inscribed angle is half of the arc. All right, so you should show your work. You should go 1/2 times 60. Even if it's as simple as that, you should at least show it, okay? And then that's 30 degrees. So that was easy. What about this one? Arc WX. Where's WX? It's this one right here. So let's make it a little thicker. That's what we got to find right there. It's not that much harder, but it's a little bit. It's not quite as straightforward as the first one. Just one little extra step. So how in the world are we going to do that? Is there an angle? Is there an inscribed angle that cuts off that arc? Like that goes to there, but that goes to there. So I don't have like one angle that cuts off that arc, do I? But I do have this. I got this angle Z, right? It goes all the way to V, goes all the way to X. So I should be able to figure out what it is from here all the way to there. Would you agree? Do you see that? What's that whole big old arc right there? It's 110, exactly right. Are you with me on that? So if you know this angle, the arc that it cuts off, which is arc VX, is 110. But that's not what they're asking for, is it? What are they asking for? WX, this little bit right here. So what do? Just subtract. So it's 110 minus 60, which is what? 50. All right, so that is 50 degrees. So it took a little thought, right? But you look at stuff that you can figure out. You're like, okay, I know that's an inscribed angle. I know that's 55. So I know that when I cut an arc off, that's going to be 110. So you write it in here. You're like, oh, wait a minute. They already told me what this little arc right here is, 60. So this is just what's left over, isn't it? From the 110. Because the 110 goes from here to here. This is 60. That must mean that's 50. We good? Yeah. The inscribed angle is not a whole lot different, is it? It's just than the central angle. It's just the central angle is equal to the arc when it's a central angle, but it's an inscribed angle. The angle is half of the arc. We good? Yes? All right, let's do another one. You guys seem dead today. What's going on? Just seems different vibe in here today. I don't know why. Let's do another circle. Copy and paste that to right here. This theorem is very similar to what we did just earlier today. All right, when we said if you have two circles and you have a central angle that cuts off equal arcs, okay, it's basically the same kind of thing, except it's not a central angle this time. Take a wild guess what it is. It's an what? An inscribed angle. Very good. All right, so let's group that. Let's copy, let's paste it, and let's get rid of that since I already pasted the circle. All right. I'm going to have to ungroup it anyway. Why is it doing that? How do I ungroup it? It's that one, I think. There we go. All right, so watch this. Oh, it's moving this. That's okay. I can still do it like this. Dumb. All right. It's taking me longer to draw this thing than it is to explain this. So watch. If that's 30 degrees, what's this arc right here going to be? 60 degrees. Okay? And if I told you that this was 30 degrees, what is this arc right here going to be? That's going to be 60. Now, these circles are congruent. I copied and pasted them, okay? You saw me do that. Well, you didn't see the Control-C, Control-V, but that's what I did. I copied and pasted. So they are congruent circles. Almost said triangles, but I said circles. Okay, they are congruent circles. So if the inscribed angle are equal to each other, what's true about the two arcs on the two different circles? So let's say I didn't know that that was 60, and I didn't know that that was 60, but I knew that this angle was equal to this angle. What could I say then about this arc from here to here and this arc from here to here? Then they're congruent to each other as well, right? And then vice versa. What's my vice versa? That's the what? No. Don't tell me what it is, but what is the word that describes the converse of it, right? Okay. So if this arc was equal to this arc, then this inscribed angle, talk to me, is equal to this inscribed angle. You got it? So if the arcs are equal, the angles are equal. Okay, even though it's inscribed, all right? But if the arcs are equal, then the angles are equal. It doesn't mean they're equal to the same number as the arc, but they are equal to each other. That's what our theorem says, okay? Now, we've got another theorem. This is kind of an interesting theorem. I like this one. We only got a minute left, but let's, I don't want to do that. Let's do this real quick. This is kind of cool. If I have an inscribed angle that's inscribed in a semicircle, so what does that mean? Give me a second. The bell's going to ring, but just give me like 1 minute after the bell rings, okay? So here's a semicircle right there. Everybody see that? What if I inscribe an angle inside the semicircle? What does that mean? That means I start at one end of the circle, and I can go anywhere here, right? And then I go from here to here. What does that look like it makes? Not just a triangle, a specific kind of triangle. It's a right triangle, exactly correct, all right? If you think about it, it kind of makes sense because, here, let's get rid of that right triangle. Let's say we didn't know what that was. This angle right here hits at this end of the semicircle and this end of the semicircle. How many degrees is that if it's a semicircle? How many degrees? Huh? 280? Oh, okay. Like you said, 280. 180, correct. So the inscribed angle is equal to what? Half of the arc. So this arc right here is 180 since it's a semicircle. So what must this be? This must be what? 90 degrees. Let's do one more and then you can go. Hang on. Let's inscribe somewhere else. Watch. What if I did there? Is there any way in the world that's still going to be a right angle? Absolutely, because we're still, even though the vertex is at a different spot than it was here, it's still cutting off a semicircle. Do you see that? So this is still going to be what? 90 degrees. So anytime an inscribed angle cuts off a semicircle, the angle, the inscribed angle, is going to be 90 degrees. All right. I think that's enough. We didn't do the examples, but I taught you all the stuff. Everybody's leaving me. Why are you leaving me? So it's page 372. You're doing 1 to 13. That's your homework right there. 372, 1 to 13. That's section 84A.